So we've been talking about the substituent effects in an electrophilic aromatic substitution reaction. And we have these activators and deactivators in this list, and we've assigned the ortho, meta, and para directing abilities of these groups. Now, what would happen if you had more than one substituent on a ring? Which one controls the Regio selectivity? Well, when you have multiple substituents on the ring, they follow a set of rules. So the first rule is that often directing groups will reinforce one another. And so in the following example, we have, let's say, nitrotoluene. And the nitro and the methyl group are in a para relationship. And let's say we're going to run this reaction in which we take bromine in the presence of iron tribromide. All right, so in order to figure the Regio selectivity of this reaction out, we need to know what the substituent effects are going to be. So a methyl group is an R group, and so its substituent directing effect is going to be orthopara because it's an activator. Okay. In the case of a nitro group, the nitro is deactivating, and it doesn't have any lone pairs adjacent to the ring, so it's going to be a meta-director. So if we were to look at where the bromine is supposed to go, the methyl group is pointing to that ortho position, and that para position, but that para position is actually already substituted with the nitro group, so we can eliminate it. Now the nitro group is directing the bromine to go at the same two positions that the methyl group already has directed the bromine to go. So those positions are meta to the nitro group. And so what this tells us is that when we're performing this reaction, we're going to get a substitution in which the two groups reinforce one another, and so you're going to get a substitution in which you monobrominate at the at one of those ortho positions. Okay, so what happens if effects are opposite? Well, that's the second case. All right, so when the effects are opposite, it is the more activating group that controls the Regio selectivity. Okay, and so let's say we have the dimethylamino and a bromine on the ring. Okay, and let's say we're going to do a chlorination reaction, so we're going to take chlorine and aluminum trichloride. And so the dimethylamino group is an activator, right? It is going to be an ortho-para director, so that's going to designate those two positions as being where the chlorine is going to go. We can eliminate the para position because it's already substituted. The bromine is a deactivator, but it has lone pairs on the bromine that are adjacent to the pi system, and so it's going to be an ortho-para director, and that ortho position are going to be right here. And so these are opposite in terms of the Regio selectivity. And so this rule states that it's the more activating group that controls the Regio selectivity. And so we know that that bromine is a deactivator and that dimethylamino is an activator. And so the more activating group is the dimethylamino. And so that's going to be the one that controls the Regio selectivity. And so we're going to do a substitution ortho to that group instead of ortho to the bromo. The last rule is that when the two groups are similar in activation, the Regio selectivity is controlled by steric issues, steric strain. Right, and the substitution will occur at the less sterically hindered site. Okay, so let's say we have a metaxylenes compound. So those two methyl groups are meta to one another. And let's say we're going to do a sulfonylation reaction. Okay, so we have two methyl groups. So this methyl group is an orthopara director, as is this orthopara director. And so that's going to substitute at this position, and that position. And those reinforce one another, but there's a key difference. This position right here is sterically occluded by both methyl groups. And so that's not going to be the one that is going to be substituted. You'd rather substitute away from that steric strain. And so one of the substituents is going to, since this is a symmetrical molecule, one of those substituents is going to have an ortho substituent to it, and that's where the sulfonylation will go. All right, so your sulfonic acid will go, let's say, here, right? And this is because the two methyl groups themselves are same in activation. Okay, so this is the multiple substituent effects. All right, you need to be aware of these when you're planning a synthesis. Now, one of the last topics we need to cover in electrophilic substitution is what would happen if you had a heteroaromatic ring or a polycyclic aromatic hydrocarbon. It turns out that nothing really changes. So heteroaromatic rings in electrophilic aromatic substitution. And what I mean by nothing really changes is you still have to draw all of those resonance forms. And so let's pose the following question. Let's say we started with pyridine, and pyridine was treated with sulfuric acid and sulfur trioxide. And I asked you to predict the product of this reaction. Okay, so we're going to have a couple of reactions that we need to draw here. So let's say we could substitute at this, let's say, ortho position, this meta position, or this para position. Okay. All right. Let's draw out what would happen for the ortho. All right. So let's say we've got this pyridine. And again, I'm going to skip ahead into the point in the mechanism in which I've got the E+, that electrophilic center. And I'm going to substitute at the ortho position right here, and that's going to give me the following set of resonance forms. So I've got that resonance form. I've got that resonance form. And I've got this resonance form. Okay, and I could, of course, lose a proton and reestablish aromaticity to give me the ortho substituted product. Like that. Right, so if I look at those resonance forms, there are 3 resonance forms. And if I look at them and I try to analyze their stability, I notice that one of them is really, really bad. And the one that's really, really bad is this one here, which has a positive charge on a nitrogen atom. Right, so it's a nitrogen atom that does not have a full octet. And so it's a really bad resonance form, so bad that this reaction doesn't happen, right? It's so slow that this reaction does not occur. Let's see what would happen if we were to substitute in a meta position. Okay, so again, I'm going to skip ahead to the point in the mechanism in which I have the protonated sulfur trioxide. I'm going to substitute the meta position, so I'm going to take that pi bond, and then I'm going to move it, attacking the sulfonic acid. And so I'm going to get this species, and I can perform resonance delocalization. And I can do it again. And then, of course, I can get a loss of a proton with reestablishment of aromaticity, and I get the meta sulfonic acid. And if I look at the resonance forms, I see that there are 3 resonance forms again. And all of them are pretty good, right? We don't have any that are really, really bad. All of them are carbocations, right? Uranium ions on carbon. And so we don't have any really bad resonance forms. Let's do the para substitution. And what we might recall from our discussion of non-heteroaromatic systems, so just regular aromatic systems, is that the para is going to really resemble the ortho substitution. And so if I were to substitute at the para position, I should have 3 resonance forms in which one of them is really, really bad. So let's see if we can repeat that. Okay, so I've got one there. Can resonance delocalize, and here I am. I've got a really, really bad resonance form. Okay, but I can continue along just to finish it out. Okay, loss of a proton would give me the parasulfonic acid, but this is so slow because you have a really, really bad resonance form that it doesn't occur. Right? So despite the fact that it has the same number of resonance forms, these resonance forms aren't quite as good. And so in this case, the meta substituent will predominate. Right? So we can draw in our little box that exclusively the product here will be the substitution at the meta position of this pyridine ring. Right, so you can sort of think of the pyridine ring itself as being a ring that is electron deficient. So it's kind of like a ring that has a deactivator on it, except it doesn't really have a deactivator on it. The deactivator is kind of inside the ring itself. Let's do an example in which we have a substituent that, an aromatic ring that is electron rich. Right, let's do furan. And so furan is going to look like this. And furan actually only has 2 positions, right, that it could substitute. So we don't call it ortho, meta, and para anymore. We call it positions 2 and 3. All right, so let's say we're going to react this with bromine and aluminum tribromide. We want to know what the product is going to be. All right, so let's say we're going to substitute at the 2 position first. Let's draw out the resonance forms for this. Okay, so of course I've got this 8 complex, so I'm going to skip ahead right to the formation of that 8 complex, the E+. I'm going to substitute at the 2 position, and so I'm going to get this resonance form. I can resonance delocalize to give me this one. And actually I can do it one more time by taking the lone pairs on oxygen. Okay, and then I can get, of course, loss of a proton to give me the substituent in which I've got a bromine at the 2 position. All right, so again, I've got 3 resonance forms, right, one of which has that positive charge on oxygen. So it's kind of like I have an additional resonance form. Let's see what would happen if I were to substitute at the 3 position. Right, so again, I'm going to skip ahead to formation of that 8 complex. I substitute at the 3 position. I'm going to get a resonance form in which I've got positive charge there. I can do resonance delocalization, only this time with the lone pairs on oxygen. All right, so then loss of a proton would give me reestablishment of aromaticity, and I've got a bromine at that 3 position. So here there's only 2 resonance forms. One of them has a positive charge on oxygen. And so because there's only 2 resonance forms, the reaction is very slow, and it doesn't occur. And so when you're going to substitute on a furan like this, you're going to give the substituent at the 2 position. So we can draw in our little box, right, that because there's additional set of resonance forms, you're going to substitute there at the 2 position. So now we have all the rules that we need for electrophilic aromatic substitution of both aromatic systems, heteroaromatic systems, and we know how to put the substituents on in a regioselective manner. And so this sort of is the beginnings of retrosynthesis using these types of reactions. So regioselective synthesis via electrophilic aromatic substitution involves a good degree of planning. So we need to figure out what the order of steps is going to be. Right, so retrosynthesis is going to involve good planning. So let's do the following example. Let's say we want to make this molecule right here, and we want to make this molecule from benzene. Well, we know that we need to add an acyl group, and we know we need to add a bromo group, but which one do we add first? Well, the first thing we should do is probably figure out how are we going to get these 2 substituents on the ring. Right? Well, how do you form the carbon-carbon bond or the carbon-bromine bond? Well, in order to form the carbon-carbon bond, we need to use the acylium ion, right? So we need to use this one, right? And that comes from the reagents, let's say acetyl chloride and aluminum trichloride. That's how we're going to get those substituents on. Okay. Now, how about the bromine? The bromine comes from Br plus as our electrophile. So that comes from the reagents bromine and iron tribromide. The other thing we need to figure out is how to add these groups on in a regioselective manner. So we need to know what the ortho-meta-pair directing ability is of these molecules. So for the bromo, we know it's a deactivator, but it has lone pairs, and so it's an ortho-para director. We know that the carbonyl is a deactivator, and so by definition it's a meta-director. And so you know that these two groups are meta to one another, and so you know that you need to put the carbonyl group on first. If you put the bromine on first, it would place the carbonyl group at the ortho positions or even the para position to that bromine, and that would be wrong. Right? So the correct order for doing this is to say we're going to take benzene. We're first going to react it with, let's say, acetyl chloride and aluminum trichloride to give us this benzophenone, or acetophenone, excuse me, right, one that has a carbonyl on it. And then because that's meta-directing, now we can take bromine and iron tribromide, and it will direct the bromine to go to the meta position. All right, let's do another example of this. Let's do the following example. So we've got nitro, bromo in a pair relationship, and we want to make those from benzene. Okay, so how do we get a nitro group on there? Nitro group goes on there by reacting the nitronium ion, again, which comes from nitric acid and sulfuric acid. How do we get bromine on there? Bromine comes from Br plus as an electrophile in this reaction, which comes from bromine and, let's say, aluminum tribromide. What are the substituent effects? Ortho-para-directing ability for bromine, meta-directing ability for the nitro group. And so if you put the nitro group on first, the bromine would go to the meta positions of from nitro. We don't want that. And so what we need to do is to add on the bromine first. Once that bromine is on there, then we can take nitric acid and sulfuric acid and do the nitration, and that nitration will go to the para position to give you bromonitrobenzene. Now there are a couple of, actually just two caveats in multi-step synthesis, and those caveats are that an aromatic ring that is more deactivated than monohalogens won't react. All right, so once we have that nitro group on there, that's a substituent that's more deactivating than a halogen, and so we can't really react this any further. Another caveat is that any group more than or equal in activation to an NH2 will actually substitute more than once. All right, so you'll actually find this out in lab when you use aniline. So it's a benzene ring that has an amino group on it. If you undergo bromination of an aniline, you will tribrominate at the ortho and para positions.